This course provides a working set of analysis data files, meshes, contour plots, and time histories to demonstrate the use of FLAC2D to conduct an advanced two-dimensional seismic analysis of a zoned embankment dam. This course is intended for experienced geotechnical analysts with significant familiarity with FLAC2D, FLAC3D, or previous versions of FLAC, such as FLAC 8.1. In part 1 of this course, a formal presentation of the modeling approach, material properties, and analysis steps was given. In this, part 2 of the course, a more informal commentary of the FLAC2D project will be provided. Note that in this course that although all data files used will be presented and the overall structure discussed, the reason behind specific modeling and scripting decisions, a critical aspect in any analysis, are missing and outside the scope and time allowed in this course. To better understand such critical modeling decisions, additional resources should be sought at the ITASCA Software Academy, through ITASCA support documents, or other resources or trainings. Let us now begin part 2. It is now time to open the FLAC2D project and explore all the related content. Here now is the FLAC model in Sketch. This model is that shown of the coarse mesh. You will also find that there will be a saved file, which will be 0. You can see this on the far left-hand side, 0_mesh_fine.sav. That will be available as well. And when that file, when you double-click on that file, Sketch 1 will open up again, and in that you would then see the fine model. Here are all the settings. If I then click here, which may or may not be set up depending on the current settings you have in your FLAC2D model, you can click here and you can see that I've defined this is shell, core, alluvium, and then if I lay the cursor along the edge, you can see the settings there. So in this, I had then clicked this button, and from that, then if I then go to, I think if I close that, open up the content, go to model. Here is the model, and if I go to construction, here is the core, the shell, alluvium. A bit odd, at least with the current settings, you have bedrock and alluvium as the same color. If I right click, set color for bedrock, I don't know, make it dark gray as an example, you can see that. One of the things that needed to be done in this model is we have PM4 sand on both sides. It's advantageous on both of the boundaries because of the free field conditions that will be later assigned, to have a different constitutive model assigned. And so in that, using the range command, just these elements on the far right and the far left have been changed, as you can see here. So there's that setting. And then if I go to some faces, you can see that there are also some along the edges, zone faces, face in 3 dimensions, really just an edge or a boundary. In 2 dimensions, you can see that provided right here with, there's construction, base, side, top, and then fluid was added in this setting, upstream, downstream, and top as well. So looking at the layout here, these are all of the data files. Here they all are here. You can also see these when you unzip the folder, you'll see these files as well. Here are the plots and the save files. Now what I like to do is add a number in front of the major files. This was not done for some of the functions or files that had functions in, which I'll talk about later. And then also with the plots as well. This allows, especially if I click here, I think you can change the order. This is nice in that it provides a set sequence of the order of the plots, as well as the saved files. This kind of serves in a similar way as in FLAC 8.1, you could set the order. So this also produces a similar type of process. So here are all the files, and so you can see them all provided here. And what I will be doing is going file by file by file as we go through it and talk about this. And so with that, you could run this one and then run the one below and run the one below as an example. What is also nice is I've added a main file, and in this main file, I just call each of these files. And so in this, if, for example, you want to just run the whole script all at once, you can go to this particular file and then click run, and it will go all the way through and run each of those. So let's start off with the very first file, static. Zoom in a little bit. And then what you'll note, and for those with experience in FLAC2D, is that here's the text file, but then if I want to, so I could then run this file. Alternatively, with the version of the set of files that I have, they've already been opened. And so in that, I can then just double click on save state. Well, this one right here. One thing that you'll note is that now, because this script has been run and saved in this save state, is that the global fish symbols have been provided here. And these will continue to be added as we go along. So what I like to do, have some type of key structure where it's easy to look at different blocks of code. So to begin, we clear any previous models, and then we restore, this being the mesh. Some key configurations here, those being for the fluid, and then also the dynamic. We're doing a earthquake analysis, and also the plugins, in this case would be the C++ models. Just to start things off, the entire model is going to have elastic. We're going to be using the elastic isotropic model. And here is for the fluid flow. Next is the location for which the parameter is going to be input. There's many different ways of doing some of these tasks. What I like to do in creating I suppose you could call it a template file, is I like specifying the material parameters in the text file itself. And in addition to that, I like storing them in extra grid variables. And the types of parameters I specify are not necessarily those that are going to directly go into a constitutive model or a parameter. So for instance, density. Instead of specifying density, I'm going to store the unit weight of the material, and then subsequently compute density and input that in. Here is our first fish function. I have a series of global variables. I've defined them explicitly as global and then specified the values provided here. And then here is the place for which I am now going to specify the unit weight of the material in the different groups. Here is the variation in the shear wave. This is the shear wave velocity at 1 atmosphere. The coefficients, the drain-Poisson's ratio, and this is where then I execute that function. Here then is I loop through all of the zones in the domain, and I am going to specify the density, the shear modulus, and the bulk modulus as defined above. I would like to bring to attention line 63. One thing here is that the shear wave velocity is a function of the effective stress, but we haven't defined the effective stresses yet. And so just to get the model going, I'm just going to I'm going to assume that the effective stress is 1 atmosphere. There's other ways that this could be done. You could do a much more complicated approach, but this just gets some parameters in there. We're then going to subsequently update these later on. Here are our boundary conditions. Fix in the X and the Y along the base. Fix in the horizontal direction on the sides. You'll note that we're fixing the velocity, but because the velocity is initialized as 0, this is the same thing as fixing the displacements. Gravity. Initially the model is dry. Here we turn fluid off, dynamic off, so we're going to be using local damping. Active, mechanical active on. Large strains are off in this setting, and then we are going to solve. That is going to determine equilibrium based on the criteria defined. So at this stage now we have a set of stresses in our model, and now we are going to, based on those effective stresses, the vertical stress, we are then going to subsequently update parameters. One of the things that I've wanted to do to be very explicit here is that after I've tested out my code, in this case, to be specific, this particular function, and everything's working correctly, I'm then going to, those parameters that I do not want to have access subsequently outside of the function, I'm going to explicitly assign those as local. I mean, there's several reasons of doing that. At least one that comes to mind is that when I want to check the values of these variables, I'm not going to want to have 100 different fish symbols to keep in mind. Also, there could be some unknowing negative impacts on terms of a variable here defined as global, then affecting something subsequently in my code. This function, this update stiffness, is actually going to be used subsequently in subsequent files. And so one of the things that currently really has no impact is that the model is currently unsaturated, 0. This is not going to have any impact, but subsequently it very well may. So, but that's computed right here. Also, not necessary, but just not to accidentally overwrite a function used in a function or a command in FLAC. I'm going to use the underscore in front of all variable names. Go through, update the stiffness, resolve the model, and then lastly, again, utilizing the extra grid variables, there are several types of parameters that are useful to check along the way. And so in focusing on those, here are several of them. Now, some of them, in looking at in each of these lines, it may be apparent exactly what they are. But let's say, for instance, extra grid variable 15. It's hard to remember what that extra grid variable is. How might I remember and keep track of and not overwrite that? So what I like to do as well, this is going down, is I have a file, extra readme, that then lists all of the extra grid variables. So you can see all of those there and what they are defined. So this is the ratio of the horizontal to vertical effective stress. This is the ratio of the shear stress divided by the vertical effective stress. This is the estimate of the maximum frequency that can be passed. Effective set of stresses that are useful sometimes, like for example, maybe you want to use the effective stresses from a previous save state in a new save state, this is useful, provided right here. This completes, and then you save the file as seen right here. A few other things I wanted to mention is that I like having my set of inputs at the very beginning of the file and not in some random location like, I don't know, line 80 is an example. And so that's something that you'll see all the way through as well. So with this now, there is a set of plots that I have added. There's 30 in total. So let's poke around at these a little bit. Now, one thing that we can do is we can click down, split to right, and now with select content, I can then click here or alternatively here. So now if I go here, and so with that, now we can see both. There's a few things that we could also do, get a little bit more space temporarily. I'm going to click the project out, and I could also go here. And so now, for instance, if you were wanting to see maybe the relationship between a command, set of commands and the plot, you can look at it that way. So if I then click down and then go to, and then click at different plots. So here is groups and some boundary conditions. Click down again. These are history locations, which aren't really applicable yet. So these are the densities at this current stage. This is not, so right now this is set as contour plots, not necessarily super insightful, but it will be helpful later on. And I'm going to go back to a separate view. So I'm going to close that, open this up, and just go here so I can just poke around a little bit so you can see the settings over on this side. So density, the difference between this and row true, so this is one of the complications when we have fluid flow turned on, the densities utilized, the densities you input need to be a, quote, dry density, and then FLAC will then compute whether or not it is, we're going to use that value or a saturated density based on the saturation in that particular zone. So something to keep in mind. And so for calculations, I have this row true. This is talked about in this is talked about in the manual or in the documentation, as well as some of the other courses that I have added on the ITASCA Software Academy. Variation in shear wave velocity. So this setting right now, if we go to zone extra, you can see that the method is constant. We could also go to volumetric averaging. That might be nice as well. Shear modulus, bulk modulus. See, there some properties. Okay, now we go to vertical effective stress, horizontal effective stress, shear stress. So K naught, this plot isn't strictly K naught at rest, but often it's thought about that way when we talk about that. So I've just retained the K naught part. It's really just the ratio of the horizontal to vertical effective stress. You can see that here. Alpha, this would be the ratio of the shear stress to the vertical effective stress, and some other plots. D vector, these are the displacements when we turned on gravity, elastic displacements, and you can, so right now the magnitude of these are set up for the earthquake analysis, which is why there's really, you're not seeing anything particularly interesting. I think the same thing is, this is set up as well. So these additional plots will become more important as we move through this discussion. Here's the first file. So next is a two-step process. Here we are now going to conduct our seepage analysis. So this would be a useful time for us to define our saturated density. Porosity by default is 0.5. I've kept that, but I've just explicitly included that in the event that that was of interest for you to change. It's important in looking at the impacts of porosity to read through the documentation from the manual. And when I mean manual, documentation can be used by help in documentation. That would be where you might look. Horizontal and vertical permeabilities in the code. These will then be computed as mobility coefficients. And we start. So there are a few aspects that, in this case, I suppose I could have had variables above to set some of the locations for these pore pressures. I've decided not to do that. So this would be something that would need to be manually changed for a different type of analysis. But here, key things I want to highlight here. This is where we then import the water table. That's a text file. And let's see, I think we could open that and look at that text file. You're welcome to do that. We then use that text file. And the reason that this is being done is down here. In this particular section right here, is that location is going to be used to help improve the initial conditions for the seepage analysis. In particular, is that the initial condition utilized is going to use hydrostatic pressure based on the water table, and also is going to saturate the material below. So there'd be initial saturation of 1, 0 above. Here's the place where the mobility coefficient is assigned, other settings. So I have added some histories at key locations to evaluate the change in the pore water pressure, and this will be talked about in just a minute. So this is the part where the seepage analysis is conducted. When you run this, it will take some time. And I want to, I feel like it probably took, well, it was several minutes on the computer that I'm currently using. The main goal of this analysis is to capture a reasonable distribution in pore water pressures. And so in that, we just want to use a value for which if I so-called made it, had a better set, or had a better, suppose it was more in equilibrium, that the, or better estimate of equilibrium, more representative of equilibrium, that really that the pore pressure distribution would not change significantly. And so in setting this value, when I was going through this problem, I found that for this situation that the pore pressures weren't changing significantly. Let's say instead of 1, I had made that 0.005. They weren't changing significantly. And so this seemed like a reasonable value to use. The cycle 500 part was here, because without this, and you're welcome to comment this out, is that it was immediately going to equilibrium, but not the equilibrium that fluid flow equilibrium that I wanted. And so I needed to, in essence, by cycling it to 500, get it significantly out of equilibrium so that the state that I desired was found. So if I click on this save state, now the results will be shown. And right now I'm just going to go to 17, which is saturation. Dry, saturated. The specific discharge is quite small, but could be reduced further. And here is the variation in the pore water pressures due to the seepage analysis. Those are, I think, the two key plots that would be important to show here. Moving on to the next two. We restore the seepage analysis. I don't need to look at the histories anymore. I'm going to be, really the histories I'm interested in have to do with the dynamic analysis. And so those are provided right here. This is the section where the density is updated. A bit of details are shown right here in the heading. I then am going to reestablish mechanical equilibrium using actually the effective stresses. Well, what is going to be done here is that I'm using the effective stresses. This is going to allow me to update the total stress based on the effective stresses and then resolve. This was the method that was necessary to produce the correct state of stress. We then solve the model. So at this stage, after line 67, I now have effective stresses that have been adjusted due to the surcharge, which is in line 53, as well as the pore water pressures. Because effective stresses have changed, I need to update the density. The RK value is important as it impacts the time steps. And so in this, that is being changed, time steps, and also we're going to need a real bulk modulus of the fluid for utilization with the PM4 sand model. This is the function that was used to find first here. And I'm just using that again because I want to recalculate these parameters. And then we save that particular state. So let's double click on that. And the other nice thing, so I'm going to go to the vertical effective stress. So if I go back and forth, so if I go through these, so this is the save state before the reservoir. Here's the effective stress. This is a problematic plot. It's outside of, or the state of stress here is problematic. It's a fairly lengthy discussion and outside kind of the scope of this particular course. But the key thing is that this has been changed to the one provided right here. This includes the surcharge as well as the pore impacts of the pore water pressure. So really when comparing the effective stresses, really switching between those two. So there's other plots. You're welcome to explore those as well. But one of the challenges with this simple approach is that we're using an elastic model. We're building it all at once. It's certainly possible that we could have very unrealistic values of horizontal stress, possibly also shear stress as well. And so in that, it's worthwhile checking the state of stress, in particular, this particular ratio, and putting some limits on what is possible, that adjustment part. That's specified here. And so in this, we then call a function. Now, I'm going to click on that one. So here it is right here. I could potentially have included this in this function in this data file here. Nothing wrong with doing that. However, I use it in a few different places, and just to make this particular data file shorter, I have just had a separate function that is in a separate data file, and you can see that I've done that in other cases as well. So in this function, we then specify the minimum value of k, the maximum value of k2. And so what it then does, I'll just quickly go through that, is that it goes through and checks whether or not you are outside of those ranges. And if it is, then what is reestablished is the horizontal stress in the x direction, and then also out of plane. You can't adjust. There's no sense in trying to reestablish the vertical stress because it's just based on gravity. And so based on this can help produce a more realistic state of stress, at least within those particular bounds that have been defined. So let's look at the impact. So I'm going to go to vertical effective stress. And if I click here, this should make no changes because that has not been changed. But what you might see a change is if I go to horizontal stress, and now I go back and forth, you can see there's been some very small changes. And those small changes, the goal here is to try to improve that ratio, which has been accomplished here. So at this stage, we hopefully have a reasonable estimate of the state of stress. It's now time to shift to constitutive models that are going to be used in the dynamic analysis. So here are the files. And what I'm going to focus on right now is the assignment of the values into the UBC HISS model for the core. In this approach, in the way that I've written this code, you're going to specify the slot, the name of the group associated with the zones in that particular slot core. Here are the parameters that have been talked about. This S_min ends up becoming more important in the shell because of the along the top, and I suppose actually on the core as well. At the very top, you could get a very small strength because of the fact that you have very low effective stresses. And this is a parameter that is then used to estimate the value of n, so that it captures or is similar to a target geometry max and damping curve. And this is then we use the function. So let's take a look at the function. Here it is right here. There's a lot there, but the critical things at the end, after all of this stuff that happens, which is consistent with part 1 of the video, here is where we specify the strengths. well, the strengths, but other parameters as well. So you can take a look at this. And there was a lot that went into setting some of these parameters, which is why there's all of the code above. And so this function is used, and it's used in a few different places. Well, in this case, actually, it's only used once for cohesive. But maybe you have multiple different types of cohesive materials. You could then use this function multiple times. So here's the shell. There's a different function. We specify the parameters as described above. And we then utilize these here. So let's take a look at that. Where is that one? There it is. Go all the way through. You can see those provided right here. Here's alluvium. These are the models for the PM4 sand model. And then alluvium 2 is the one on the edge. And so just a very simple, just a strength of 1300 was assigned along the boundary there. And so with that now, if we look at the results from that model, I'm going to click on that save state. And let's just go right here for the time being. I zoom in and I use the show detailed information. Maybe click right here, zone. You can see model UPC hist, model PM4 sand. In looking at the state of stress, and let's look at the ratio of the horizontal to vertical effective stress as an example. If I go back and forth, you can see that there's some slight changes. Just to double check that there isn't anything unrealistic, we are then going to reutilize really the same code above, but down here. Here you see it right here. We do that, and with that, here's the K naught again, or the calculation of K naught, then adjust, or the ratio of the horizontal effective stress to vertical effective stress. And at this stage, we're almost ready to do our dynamic analysis. That's in dynamic setup. Key things that we need to do in this part of the analysis is that we have simple constitutive models. If they're supposed to behave undrained, we need to update the bulk modulus of the fluid to be representative of a undrained bulk modulus. That's done here. Specify Rayleigh damping. Just a little bit of Rayleigh damping is going to be utilized because we're using the UPC hist model and the PM4 sand model, which have hysteretic damping included in it. We reinitialize first call, which is necessary in the PM4 sand model. We're going to use a real bulk modulus of fluid in the alluvium. I'll show you that in a minute. We set the displacement as 0, velocities as reestablish. We set the displacements and velocities as 0. We free the velocity as well. Set the model large on. Let me zoom in a little bit. You can also see that there's many more global variables. I've now defined some extra grid variables to do key things. This is representative of the excess pore water pressure ratio, the maximum excess pore water pressure ratio, engineering shear strain. It's a subsequent function where I can then define the excess pore water pressure ratio for a particular XY location. And then here are all the histories that have been utilized for different locations in which all should be showing you, and then we save it. So let's take a look at that. A few things that I want to, let's go to, so here's the model. It's about to be set up. There's the history of locations that you can see now, a horizontal and vertical array of values of history locations. This is the maximum Fmax. This is the maximum frequency that you can pass. This is problematic. It's because the model is too coarse. This is why the fine mesh was defined, because this is not going to be sufficiently accurate. The results will still be interesting, but for an actual project, you would want to use a much finer mesh. But the nice thing about this is something that you can all run whether or not you have yet to purchase a version of FLAC2D or not. This is the plot I wanted to show. So a zero bulk modulus of fluid anywhere except for the alluvium. That's because we don't want the pore pressure to change during the dynamic analysis in the core or in the alluvium, because we don't believe with the UBC HIS model, which is true, that we can accurately capture changes in excess pore water pressure. Now it's time for the actual analysis. I import the different time histories. The one that we're going to be utilizing to calculate, we're using a compliant base approach. So this velocity is going to be multiplied by the shear wave velocity times the density in the bedrock, which is representative of the basement layer. The coordinates provided here. So this is where the shear stress is applied at the base. Quiet boundaries are applied along the sides, along the base provided on the model. So this the bottom side, the bottom, so that'd be line 33, and free field boundary conditions. I have set that the maximum time step cannot exceed 1 times 10 to the minus 5. It can be smaller, but can't be larger. And here is then, this is something of importance, that you should be checking as well. So the FLAC is going to compute a dynamic time step, but there are times, especially based on the constitutive model being utilized, where you might need to further reduce that time step. And now we're going to save the model for the duration of the shaking. So now we're going to spend some time looking at these different plots. I'm going to click that so we have a bit more space. Okay, here is the model, and one thing you'll see is that it has deformed. So if I go back and forth, this is before the earthquake, after the earthquake. It's including the free field conditions on the side, so we can take a look. But really, I want to start looking at is, well, we could look at the vertical effect of stress. So one of the things that you should see going back and forth is that, well, the effect of stresses have significantly decreased in the alluvium because of the generation of excess pore water pressure. But going through, here's D vector. Now you can see the deformations due to the earthquake shaking. Here are the displacements here's displacement in the horizontal direction, the vertical direction. Here is the maximum shear strain increment, maximum shear strain. Slightly different. This is an extra grid variable, the engineering shear strain, plus or minus. So what we're looking at here is the pore water pressure ratio at the end of shaking. There's no dissipation, and I'm going to show you a time history in a minute. But here are the values that you can see here. So we're reaching a value close to 1, in some cases slightly larger in the alluvium in certain regions. And this is the maximum during shaking. So now the last plots are all time histories. Here's the input motion. You can see the different plots, and if you click here, you can see the settings on how I produce these various plots. It's a great new improvement over FLAC 8.1 to produce plots like this. So here are the acceleration, velocity, displacement. This is comparing, the blue is the velocity time history that was input. The red is the value being calculated at the base, which are going to be quite similar for this particular model. Here is the displacement. I've picked 2 places, the crest and at the base for comparison. So here's the crest, red, base, blue. Although there's, and the mode of movement or the mode of deformations for this particular dam, it's certainly moving back to the right and left, but along the crest, you have the embankment deforming downstream and upstream. And so almost it's like they kind of cancel each other out a bit at the end. Whereas if you look at this vertical displacement, you can see that you're accumulating 0.35. Let's just double check that I'm reading that right. So we go here, and maybe I click that node. So vertical displacement. Yeah, right. Minus point, so 0.3. So third of a foot. So there's displacement. No, that's not the right one. That's vertical displacement, but going down. All right, what else? So what we're looking at here, this is engineering shear strain at a few key locations. This is in the core. The red is the left shell, the right shell, the left alluvium, the right alluvium, the locations being shown here. And then also what we have is the generation of excess pore water pressure in 2 locations in the alluvium, that the same locations as the shear strain that you see, engineering shear strain above. So you can see the generation of excess pore pressure. There is, of course, no dissipation again. So this is just due to changes in volume, which then will relate to changes in excess pore water pressure during time. Here are the stress-strain relationship for the core, shell upstream, shell downstream. This stress-strain relationship, you can see that it definitely looks more realistic than if you had the Moore-Coulomb model, which would be elastic, perfectly plastic. But you can see the accumulation of strain in each strain and changes in stress. As well, you can see there's definitely reaching the yield strength in the core, which comes out here. And the last time history is the alluvium. The upper plots is stress strain. Sorry, not the upper plot. The first column is stress strain, and then stress path as well for those locations. One of the things that was mentioned in part one of the video was that the PM4 sand model, the residual shear strength, which may be familiar to some of the listeners, is not an inherent property. And so what's often done is a post-earthquake analysis for which let me go to a particular plot, for which the idea is that if you have calculated high excess pour water pressures in particular locations, for instance right here, this might be a place for which, based on previous case histories, the shear stress could potentially be reduced down to the residual shear strength. And so what's done is that in this last part of the analysis, we're going to check particular zones for some type of criteria. So for instance, maybe the criteria relates to excess pour water pressure, maybe the criteria is associated with some type of shear strain. And in those in those zones is that the material strength is going to be reduced to a residual shear strength. And to accomplish this, we're also then going to switch to a simple constitutive model, that being the Moore-Coulomb. That is the last stage of this set of analyses. So here's right here. This is the residual shear strength. What we're going to say, if it is in excess of 0.7 pour water pressure ratio, this is the maximum value that was calculated during shaking. We're going to convert to the Moore-Coulomb model. And the key thing, we go back to a static type of equilibrium. This is what we're going to be calculating here, gravity-driven deformations. One of the things that's going to be important is that we're not going to use local damping. Could potentially impact the results. Instead, we're going to just use stiffness proportional damping, just a little bit of Rayleigh damping. And here is the place where we're going to convert to the Moore-Coulomb model, side and residual shear strength, and run the model for 2 additional seconds and check the results. So what we can do is go here. So here is the group. So I'm going to just temporarily show just for a moment. I'm going to change this from group to model. And what you can see here is that most of the alluvium in this particular case did have an excess pour water pressure ratio of greater than 0.7. Not in some of the locations here. This is due to the static shear stress in those locations before shaking, the lack of stress reversals. But you can see it in this case. And so the reason being, cayenne color is Moore-Coulomb model, PM4 sand, so you can see the zones that were changed. So let's go back to the group. Now, in this case, in this model, we can look down, we go down to displacement, let's go to vertical. Let's see, was there any impact? So I go back. I'm clicking back and forth, and although we have a much lower strength in that material, it is already deformed significantly. And because of that, the new configuration of the dam is such that there aren't additional appreciable deformations. I also wonder is if we reran the model and instead also in this region that does not have that low strength, possibly if we reduce the strength down here, it could continue to move. But this is the advantage of us having done this more complex dynamic analysis, because based on the state of stress, the expectation is that the material is not liquefying in this particular location because of the lack of stress reversals. Another place we can look at displacement. And so if we at least go back and forth, you can see that it'll change the other 2 seconds. There is no appreciable increase in deformations here. This completes part 2, a more informal commentary of the FLAC2D project. To better understand the modeling and scripting decisions inherent in this work, additional resources should be sought at the ITASCA Software Academy, through ITASCA support documents, or other resources or trainings. Thank you.